Okay, so today we are going to talk about manifold. Basically, some general mathematical concepts or concepts in differential geometry. And the reason why we are going to talk about it is that as we learned in the discussion of nonlinear gravity, we learned that now we are not dealing just with Minkowski space-time. We thought that we have to replace the Minkowski metric with a new metric, which is not dynamical and it can change over the space-time. So therefore, the notion of lengths and angles will also won't be the same as in the case of Minkowski space-time. In general, we are dealing with curved space-time. So we have to generalize the notions that we were working with in Minkowski. Many of the things must be familiar. They are, in fact, some of them we have already used implicitly. So here the goal is to formalize them a little. Okay, so we go from eta mu nu to g mu nu. We go from the Minkowski space-time to something more abstract object or space, which is called manifold. Well, in fact, to define manifold, we don't even need to talk about the metric. The manifold is just a generalization of the flat metric, flat space-time that we have, or just flat space that we have. And the idea is that we consider some more general spaces which can be covered by a bunch of charts. So these are some maps from the different regions of these objects. Say it's the surface of some surface of a potato or a sphere. And whenever we can find a bunch of maps from that surface, or in general in higher dimensions, we can find maps from that to flat space to describe that space, then we call this manifold. So there will be one map that covers part of this, and there will be a map that takes points on this region to points on this in this part of the Euclidean space or flat space, and then there can be another map here, x prime, y prime. So essentially the idea is that now we are going to talk about spaces that can be addressed by a set of numbers or coordinates. So they can be coordinatized. Like the surface of the Earth, we can have maps that for different countries on the Earth, and then these maps can have some overlap near the borders. And in each map, we use a set of numbers to identify different points. So this is like the definition of manifold. Let's consider a concrete example. We can consider a sphere or a two-sphere. So how is it defined? Usually it is defined, or it's easiest to define it by embedding it in a three-dimensional Euclidean space. So if I have a 3D Euclidean space, then a two sphere is defined as the surface which satisfies x squared plus y squared plus z squared equals to, say, imagine it has radius 1. So it will be the surface that satisfies this condition. Now, how do we address different points on this sphere? There is no unique way. There are various ways of doing that. One way to do it is to divide it into various hemispheres, and then use the coordinates of this embedding space to identify different points. Note that there cannot be one coordinate system that covers the whole sphere. So what we do, for instance, is that we cut it into a hemisphere along the z equals 0 surface, and then the points on this hemisphere plus z hemisphere can be just identified by the x and y coordinates. So we just project it down on the xy plane. So every point on this hemisphere is assigned to two values of x and y. It's a two-dimensional, so the dimension of the manifold is determined by the dimension of this set of numbers, or the size of this set of coordinates that we have to use to identify various points. So in the case of two sphere, that 2 means that it's the two-dimensional sphere. So we need two numbers to identify points. So this will be one map that covers the upper hemisphere in z direction. There will be another map that covers the lower hemisphere. And then we can consider also different cuts that goes along the x equal to 0 plane and y equal to 0 plane. So there will be 6 of them, which are enough to cover the entire sphere. So yeah, I guess the important lesson from here is just the fact that you cannot cover the whole thing by just one coordinate system. In general, unlike the Euclidean space or Minkowski space, in which we had one coordinate system that covers the entire space-time, here in general, we need to have various maps or various charts that overlap, and then the combination of those together will cover the entire manifold. In general, it's not possible to cover everything. Yes.
In this sense, the hemisphere is not the manifold.
No, the hemisphere is just a part of a subset of the manifold. I guess you could define a different manifold, which is just hemisphere, but then it would be a manifold with a boundary. So that would be a different manifold, if you like. But if you want to talk about two sphere, then and then that manifold can be called the hemisphere. If you just consider the hemisphere by itself as a manifold, that could be covered by a single coordinate system. But if you want to describe the full two sphere, then you need multiple or more than one.
Yeah. Is there a relation between the minimum number of maps we need to cover the whole manifold with the dimension of the manifold, or the dimension of the map, or not the map, but the space we're mapping it?
No. Well, take the example of the flat Euclidean space.
Okay.
The minimum is always 1. But then depending on how curved your manifold is, or what is the structure of the manifold, then it can be more.
Is it desired to only have one map to cover the entire manifold, or is not? There is no problem. Like.
But sometimes it's useful. I guess when you see, sometimes it's useful because you, for instance, you might want to talk about someone who travels through the entire manifold, and then if it is possible, then it would be nice because the whole trajectory is described in one coordinate system. But it's not always possible. Sometimes it is desirable. Like for instance, you will see, probably you will see the case of the short sheet solution, and then there will be the short sheet coordinates that do not cover the entire solution, while there are other coordinates like Pine-Levy or Kruskal that covers the entire. And the nice thing about those is that you can describe the infalling observers into the black
For example, in the two-sphere, there is also this stereographic projection.
Yeah.
But that one does not cover the North Pole, only that point.
Yes.
And then in this point, we need to map it to another space also. Like how?
Well, if you want to use a stereographic, then let me just say what the stereographic map is. It's a different kind of coordinate system for the sphere, which is defined by putting this sphere on a plane. I think it has a two-dimensional plane. It's a surface of a table. So you put your sphere on this surface, 2D surface, and then you sit here and then draw a straight line. And the coordinate that you associate to every point of the sphere is where it crosses this two-dimensional plane. So this map covers the entire sphere except the North Pole, where you are sitting and doing this column. If you want to find a complete, what do they call it, atlas? It's, I think, the complete set of charts that cover the sphere. You can combine two of these stereographic maps. So one from the North Pole and one from the South Pole. And then the combination will cover the whole. Okay, now another novelty of this new situation, these non-flat spaces, is that is how the notion of the vector or displacement changes. So when we talk about Euclidean or Minkowski space, there is a Minkowski. we have a notion of the displacement vector. So if I take point A and point B, then there will be a displacement vector delta x a b mu, which is just x b mu minus x a mu, and this is a vector in Minkowski space. For any xa and xb, so they can be finitely separate from each other, and you have this displacement vector. And moreover, we can put this displacement vector at any point. Now we could, this vector is identical to one that we can just draw at the origin. So in a sense, the vectors that we don't need to base our vectors in flat spacetime on particular points of the spacetime. They can live anywhere. It's this displacement vector is a universally defined vector in this Minkowski space. Now this is no longer correct if we have a general manifold. There is no way we can take, for instance, the surface of a sphere and two points and then associate a single vector, a single displacement vector in a unique way. And moreover, and this is related, the vectors that we want to define, they cannot be universally defined. So what can we do if we want to have a notion of vector on a sphere, on a general manifold? What we can do is to use the fact that if we consider infinitesimally separated points, then for those it does make sense to talk about a vector. So as I take this point very close to the other one, then it's like some little creature that live on the surface of the apple, who do not realize that it's not a flat manifold. So for them, a small displacement can be, they basically can use the notions of the flat spacetime, associate a vector to that small infinitesimal displacement. However, that vector only lives at that point. It cannot be associated to some other, or it cannot be defined universally. So what we can do is that we can draw some tangents in spaces at different points. And then infinitesimal displacements correspond to vectors in this tangent space. So this tangent space is a piece of the flat, or not a piece, it's an entire flat Euclidean or Minkowski space that live at different points. And then vectors would be objects that live in this tangent space. And then now from here, it's kind of obvious that there is no obvious way of connecting vectors which live at different points. So they have to be based at different points. We would talk about a vector V that lives in the tangent space. Like about a vector V that lives in the tangent space of a particular point, say in this chart point 0 and 0. And then the vector V prime that is an element of the tangent space of a different point. say the point, I don't know, 0.5. So it's important which point they are based on. Okay, so how do we define them? I guess the easiest way to define them is basically what we have been doing so far based on the transformation properties. So when we have these coordinate systems, we can have regions when they overlap. And we can, for instance, ask we can define vectors in terms of their components. So the vector would be a d-dimensional object. It has d components, and then it's defined by a particular transformation property as we go from one chart or one coordinate system to the other one. That's the way we learned it the first time. Yes.
In the beginning, we said that in Minkowski space, you can move the vector from like you can. It's basically like clean, but when you have different frames, different reference frames with the relative velocity. Let's say maybe the length of the vectors and the notion of maybe the coordinates and the space will be different for them, right?
Yes, yeah.
So why we didn't speak about this also in Minkowski space because
no, that's true.
I think also when you talk about gravity or about a reference frame where you have more energy or more mass, it's also yes. It's make your coordinate also change.
Yes, so in fact we do talk about changes or how the components of vectors change when we go from one frame to the other, even in special relativity, even in Minkowski. Those were the Lorentz transformations that we talked about. So it's true that if this notion of vector and defining them based on how they transform, that is also true in flat space. Or in Euclidean, for instance, we talk about rotations and how the components of a vector change under rotation. What I wanted to say was that in the case of flat space, you have a single coordinate system that covers the entire space-time, and in that coordinate system you can universally define a vector. So you don't need to say this is a vector that lives at this particular point. A vector in Minkowski space it can live anywhere. And the reason is really that these tangent spaces, they are all identical. I mean, Minkowski, they are in a sense they are all parallel.
Okay. But I mean, we still here also like physically we're talking about, for example, you can say like about solar system. You have this manifold in the solar system. You're speaking in that generality, or you're speaking when you say manifold, you're meaning the entire universe.
Well, I'm not 100% sure what you are trying to ask.
I mean, when we're saying the coordinate, when we say the set of the coordinates, we are talking like in general that your whole coordinate are not no longer Minkowski, and they are in some manifold. And when you talk about this manifold, you mean the universe, or you mean the like in any place in the universe you don't have that Minkowski space?
Well, you can do both.
Yes, it's both.
Can do both. I mean, if you talk about the whole universe, it means that you want to discuss what is the general global properties of the manifold. Like for instance, in the case of a sphere, you have the idea that you can go around it and come back to the same point. While you can also discuss the patch of a part of the sphere, and still all of this discussion holds, because even that patch of the sphere is not flat, so you cannot define vectors universally. So we don't have to know or discuss the global properties of the manifold in general. Although in principle you can imagine that there is some manifold with some global properties.
But I'm still trying to understand the consequences of making delta mu nu to j mu nu. I mean, is it just like just saying that when you have energy and gravity, you just change your coordinate? Is this all what it says, or we are?
Well, the consequence is that now we are not in Minkowski. We are not in Minkowski spacetime at the moment. We are not in the flat spacetime. Then we have to understand geometry of non-flat spaces a bit better. So, yeah, what about the vectors? One thing that, so the way I talked about vectors here was I talked about infinitesimal displacements on the surface, and how I can assign to those infinitesimal displacements a vector. Now, the moment you define a vector like that, you can now talk about how it acts on functions. So imagine you have a function on this manifold, say on this sphere. Function is what? It's a map from, so in this case it's a map from x and y to real numbers. To every point on the sphere, it assigns a number. Say this function is smooth. Then these infinitesimal displacements can, or these vectors naturally act on the functions by taking the derivative of them in this in the direction of that displacement. So if I'm saying that the vector v corresponds to some particular displacement, infinitesimal displacement on this manifold at this point P, then I can think of acting by this vector v on a function. And that is just going to give me the derivative of the function along that direction. Now, once we talk about this the vectors in the following way, then it makes it clear that we can think of the mu's partial derivatives with respect to our coordinates as a basis for the for the vector field. So in general, we can expand vectors in terms of partial derivative. So we should think of this set of d mu's as a set of as a basis to expand v's, and then we can choose different charts or different coordinate systems. And once we do that, the components of the vector will change accordingly. So the vector is some invariant object, but in any coordinate system it will have different components. And now you can see that it actually, this definition reproduces the transformation properties of vectors that from the past. Given that, so we are going from coordinate system x mu to x tilde mu. So the derivative d tilde or d by d x tilde mu is dx dx nu dx tilde mu d by dx nu. So if we use this relation, we get v tilde mu is equal to d x tilde mu dx mu v mu, which is the usual transformation property of the vector. So another related thing that we can do is that we can consider curves. Maybe this is too easy. We can consider curves. Which are defined as a collection of x mu's, which are parameterized by some. So it's a trajectory in our manifold which is parameterized by some real number. So as for instance, as sigma goes from 0 to 1, then these points x mu, they go from here to there. So say from P to Q. Of course, I'm assuming that there is this whole trajectory is covered by a single chart when I write this relation. In principle, I can consider a curve that travels between different charts, and then it will have different. Well, I have to use the coordinates associated to those different charts to describe. So more mathematically, it's just a map from real numbers to the manifold. You can give it the definition which is independent or invariant doesn't uses the coordinate system. But it's easier to talk about the in-coordinate system. This is something that we have already talked about or encountered before. We were talking about word lines, and those were curves in those are curves in Minkowski spacetime. So this is just a generalization of that. So before we were talking about some observer who would move along some trajectory x mu of sigma. This is the same thing, except that now we can also define such curves on general manifold. It doesn't have to be flat. Now, when we have a curve, then it defines a set of vectors. At every point that it passes, it defines a vector which is called the tangent vector, which is dx mu by d sigma. So in particular, in the case of word lines in Minkowski spacetime, we said if we parameterize or trajectory by the proper time, then that tangent vector, so that then in this case it would be x mu of tau, and then the corresponding tangent vector would be what we call the forward velocity. As you see, in general, the tangent vector is related, is sensitive to how we parameterize the curve. So if I were to parameterize it by a different parameter, like say twice, something that runs twice faster than the proper time, then the length of this tangent vector will be different. Okay, so this is the tangent vector and the forward velocity. And then we can also talk about vector fields. So as you see, I'm just listing a bunch of definitions. There is nothing particularly sophisticated. Most of them are things that we have seen their analogs before. So what about vector fields? The vector fields are like electric field. So it's just it's an assignment of the vector to every point on the manifold. And then what we can do is that if we have a vector field, if we have an assignment of a vector to every point on the manifold, we can construct field lines, like electric field lines. So we can start from one point, see where the vector field at that point is, move along that, then we arrive at the next point. We find the value of the vector field at the next one, move along that, and continue. This gives us a curve that does not cross itself. Right? Remember that electric field lines, they do not cross. Unless the vector field vanishes at some point. Because if they cross, then it means that the vector field has two values at a different point. But well, if I guess here I implicitly assume that we are talking about a single value vector field. So as long as it is single value, they cannot cross each other. Single valued and non-vanishing. So what is the example here? Say for instance we can consider the sphere and talk about the latitude. The latitudes are just lines of constant. On a sphere the latitudes are lines of constant theta. So if we use the theta and phi coordinate. So this is theta, the angle between the point that we are considering and the z-axis, and then there will be phi, the angle between its projection and the x-axis. So the latitudes are lines of constant theta, and so on. And these are curves. We can have from every point on the sphere there will be a latitude. There will pass one and only one latitude. So we have these curves, and as we saw, every curve assigns a tangent vector to the point through which it passes. So if we consider these latitudes, they will define a vector field on the sphere, except for the North Pole and South Pole. And that vector field is just something that is just a tangent to the latitude at every point. Now, if you imagine that you take these curves and parameterize them by phi, so latitudes are constant theta. If I parameterize them by phi, then the tangent vector to these latitudes will be just defined, right? It will be just a vector that moves along phi. And so this will be our vector field. It's just a vector v equals d phi at every point on the sphere. And we can also talk about longitudes, which are curves of constant phi, and similarly they will introduce a vector field on the sphere. Now, if you have two vector fields, now I want to talk about the Lie derivative. If we have two vector fields or several vector fields on a manifold, one natural question to ask is, can we use them as a coordinate system, at least in some local region? Like for instance here, can I use this vector field associated to longitudes and latitudes to coordinatize this sphere? And we know that the answer is yes, we can use a theta phi coordinate system to cover this sphere, again, except in North and South Pole. But in general, so the question is, let's say we have two vector fields. So the question is, what is the condition to be able to use this vector field as a coordinate system? So what does it mean to use it as a coordinate system? What it means is that I want to choose, say, some origin, and then say if I have this two-dimensional manifold, I want to associate to a general point in here, say this point P, I want to associate to it a set of two numbers, T and S. And what is the meaning of these two numbers? The two numbers tell me how, starting from the origin, how much should I travel along the vector field. So let's call this vector field T, and this vector field S. So this collection of two numbers, T and S, tells me how much should I travel along T and how much should I travel along S to arrive at that point P. Now there is a condition for this to be possible, and that condition is that this assignment of the number should be independent of the way I choose to travel. So for instance, if I go with parameter T along this vector, so what does it mean to move along with parameter T along this vector? We have a vector field. In order to so the vector field assigns a vector at every point. So there will be a vector field here. So what I do is that I take my dx mu dt to be t mu. So I start from here and I move for the amount, some amount, finite amount t. So I arrive here. And then I start moving along S. So I arrive here and then I move along S so that I arrive to this point P. The condition that this vector field can be used as a coordinate system is that if I were to do it in a different order, say I go here first, I first travel along S, the parameter little s, and then travel to along T, I arrive at the same point. Now generically this doesn't happen. Generically, if I have some two vector fields, if I travel along two different paths, so let's make the paths smaller. Let's make it smaller. If I move some infinitesimal amount along T, so say I move by some dt and then by some ds, and then I do it in the other order, ds and then by dt. First go there, go here, then these 2 points will generically be different from each other. And the difference between these 2 points, so this is an infinite, if I take these transformations, these movements to be infinitesimal, those 2 points will also be infinitesimally close to each other, but not identical. So they define a new vector for me that connects the two.
We can define a vector because the displacement is infinitesimal.
Yeah.
Otherwise we could.
Yeah. So in a sense you can do it in the limit in which you send this dt and ds to 0. So what the requirement that we can use these two vector fields as a coordinate system is that this new displacement vector has to vanish. Now what is the general expression for that displacement vector? That is something that is called the commutator of the two vector fields, or the Lie derivative of one with respect to the other. It's called commutator for an obvious reason, right? We do first one and then the other, and then we do it in the opposite order and take the difference. So say we call them, I call them T and S, so we talk about the commutator of T and S, where T and S are vector fields, and this one defines a new vector field, so it will have some index. And that is d nu s mu minus s nu d mu. So this is exactly what I described here in the picture. This displacement vector is exactly given by that. So this is a commutator, and if it vanishes, then we can, if it vanishes everywhere, at least in some region, then in that region we can use these two vector fields T and S as a way of coordinatizing the manifold. This is also called the Lie derivative. So this is called the Lie derivative of S with respect to T, which is again a vector.
This is just to say that both fields are changing by the same amount. Like they are, for example, having the same, let's say, changing of time or with length. Is it or it's not?
No, I wouldn't say they are changing by the same amount.
But why we didn't speak about the direction of them? Because, for example, in some regions, maybe we will have both fields in the same parallel to each other. So in that regions, how we would define coordinate?
Oh well, yes. If they are parallel, then they can be. The commutator can vanish if they are parallel, but then they would give a redundant coordinatization. So no, it's true that you cannot. If they are parallel, you can. So there is an extra condition that I didn't say. They have to also be linearly independent.
All the space, over all the space.
Or in the region when you want to use them as the coordinate. Yeah.
Is it a problem that the latitude vector field vanishes at some points that we cannot?
Well, it tells you that you cannot use these theta and phi coordinates at every point. Like it's not a good coordinate, it's a singular coordinate system for the north and south pole.
If I want to calculate the Lie derivative according to that vector field, at that point I couldn't evaluate.
Yeah, well, yeah, at that point it vanishes. So this is again, it's a bit similar to this requirement of being linearly independent. If a vector vanishes, then it cannot form. If one of your vectors vanishes, it's not linearly independent from the other one, because it's 0 times the other. Okay, so then we move on. We talked about vectors and vector fields. We are also familiar with other objects like tensors or covectors, which were just covariant vectors, where they were objects with an index, with a lower index. So again, the one operational definition of those objects, first of all, the idea is very similar. The same way that we have now tangent space that belongs to different points of the manifold, now we can have in those tangent spaces we can have higher dimensional tensor fields. We don't need to just discuss vectors. So for instance, starting from the vectors, we can go to the covectors or covariant vectors.
Sorry.
Yes.
This Lie derivative is like just the vector connecting the 2 points, like.
Yes. This is exactly this vector.
That vector. Okay. Okay. Sorry.
No.
Just. Like it exactly in flat space will be T mu minus S mu, like normal, because those derivatives will be 1 in flat space.
Sorry.
In flat space will be just the difference of the vectors. If we go in one direction or in the other, like.
Why did you say? No, I didn't understand.
They're just saying that this is the difference between the 2 points when we go, because we go in one direction, then in the other, or doing the other, we don't arrive to the same point.
Yeah.
So we have this difference between them, and
Yeah.
that's that vector.
Yeah.
Okay, so in flat space it doesn't happen that, because in flat space we will arrive to the same point. If we go first to x, then to y.
Well, no, it's the property of the is the property of your vector fields.
Oh, okay. So it is
So it's not a signature of the curvature of the manifold. It's some property of the vector fields, whether they.
the parameterization.
It's basically, it's exactly this geometric notion. You have these two vector fields,
Yeah.
and then you move by some amount in one direction by dt, and then by ds in the other direction,
Right.
and then you do it the other way.
In polar coordinates, they may give different results even in the flat space.
What called?
In polar coordinates, if we do the different directions, maybe we end up at a different point, even we are in the flat space.
Well, no, because the moment you say coordinates, then
I mean,
by
vector
construction it's
Vector fields constructed by d of with respect to r and d with respect to the theta, they make the vector field lines.
right.
And if you do the same thing on that vector field,
Yeah.
maybe we end up at different points.
No, no. In that case, well, if you talk about the polar, whenever you say coordinates, it means that you have already satisfied this requirement because you were able to construct a coordinate system using those vector fields. So if you take the polar coordinates in flat space, they will actually commute in a sense that if you choose different paths, you will go to the same point. However, you can easily construct vector fields that do not satisfy this property. So let's see what what is an easy way to do it? Just take one vector field that does satisfy the property. And then it's kind of easy to make it not to satisfy. So let me just give you an example. So for instance, on a plane, on a Euclidean plane, we can have the simplest thing to consider is x and y. And the associated vector fields are dx. So then we have t equals dx and s equals dy. These two vector fields, they commute, and they therefore they can use as a coordinate, as you all know, to parameterize the plane. Now consider the following. Consider a new vector field which is parallel to this t, but its length is now y-dependent. So say my t prime is just y times dx. And s is the same. Now they do not commute. Right? So if you calculate...
Can we draw that?
Oh yeah, I can draw. So this look like, well, they look like the same as x and y field, except that what happens is, so say we are at the origin. Now at the origin, note that this is even it's even singular. So this vector field you cannot even use it as a coordinate. So let's go to not the origin. Let's go to the point y equals 1. So this is the origin. At this point, this t prime is singular. We cannot even use it as a coordinate. But for instance, at y equals 1, you can use it. So these are supposed to be x and y. Now, what is going to happen? If I try to move along t prime with some infinitesimal parameter here, and then move along s by some dy, so I will go there. Let me just draw it bigger. Now, let's do it the other way. Let's first move along s. So s is dy. So this is s. And this is t prime. Right? S is the vector that points in positive y direction, and t prime is the vector that points in at positive y, it points along positive x direction. At negative y, it points along negative x direction, because it's proportional to y, so when y is negative, it points in the opposite way. Okay, so now we are trying to do this set of movement. So at y equals 1, I do two things. First, I move by some parameter, say 2, along t prime, and then by a parameter 2 along s. And then I do it in the opposite order. I move along s by parameter 2. It will be the same thing because s doesn't. However, now if I move along t prime by parameter 2, now you see that t prime y here is 3. So moving by parameter 2 along T prime is equivalent to moving by parameter 6 along X. So therefore they do not commute. Now
it's 2 over 3, right? Because you wait.
This is supposed to be 6.
But 6 for no. You want T prime to be 2, right?
Yeah, but now at y equal 3 you will move 3 times as much as when you were at y equal 1.
We want y prime to be 2, right? And we have y equal 3.
But we don't, I guess what I'm doing is I'm just doing the same amount of displacement along T prime. The same amount of displacement means that I take dx mu dt to be T prime mu, and then I integrate this for delta t of equal to 2. But since T prime is at this point, T prime is just 3 times
Times 2.
3 that is 3 0. Then if you integrate this for parameter 2, your delta x mu will be 6 and 0. Six, I guess, will be here. Now, if you do but this was not an infinitesimal transformation, but it shows clearly why these two vector fields do not commute. And it has nothing to do with the curvature, it's just the fact about these vector fields. Tensors. Yes, so I was saying we can, once we have vectors and these tangent spaces, we can also define tensors in those tangent spaces. And we can also talk about covariant vectors or covectors. So again, the easiest, the operational way to define it is based on the transformation properties on the coordinate change. And this is what you are familiar with, right? We said V mu transforms, as we said somewhere. Now we can talk about covectors with a lower index and the transformation property. It's just what is dictated by the having a lower index. And then similarly, you can talk about tensors with as many indices as we like, mu1 to mu-n, and then we can have mu1 to mu-m. And then the transformation property of this is just take n t tilde will have n dx prime by dx and m dx by dx prime. So it's kind of a trivial generalization of vectors. However, we can also give a more coordinate-independent definition of these tensors and covectors in a similar way that we gave a coordinate-independent definition of vectors as objects that act on the functions. So we said a vector is an entity that it acts on a function and gives a number. And that number is just a derivative of the function along some direction. Times some other number which is determined by the components of the vector. Or we don't really need to talk about the components. Any vector would define some displacements, and then the action of the vector on a function would be really just the difference of the function between those 2 points. As long as it is infinitesimal. So now we can talk about the covectors, or covariant vectors as entities that act on the vectors that give numbers. The number that they associate to vectors is basically their inner product. So if omega acts on a vector v, omega acts on a vector and gives a number. That number is just omega mu times v mu. So they can be naturally defined as the map from the vectors, the space of vectors, or tangent space to R. To be more precise, in the case of vectors, the vectors can be defined as a map from the space of functions to R. So we have the map from the space of functions to R, then we have the map from the space of vectors to R. And then the higher rank tensors are defined in a similar way. So if, for instance, a tensor, a covariant rank 2 tensor will be a map from the space of, from 2 vectors, v1 and v2, to R, to set of real numbers. And in components, it's just T mu mu times V1 mu V2 mu. Now, a particularly important tensor is one that is essential to talk about local properties of the manifold is the metric tensor. That's the object that allows us to associate lengths and define angles on the manifold. So what is metric? Metric is one of these tensor, is a covariant tensor, a rank 2 covariant tensor that has some properties. It has to be non-singular. It takes 2 vectors again and gives a number. And it has the property that it is invertible, meaning that if G of V and W is equal to 0 for all W's in the tangent space, some point P, then it has to be that V is equal to 0. This guarantees that we can find an inverse for this tensor, which is the inverse metric, and we usually show this inverse metric by the same sign, by the same symbol. So usually we just show it by the same G, but with upper indices. So what is this property? G mu nu, G nu lambda is equal to delta mu nu, like mu lambda. So it is inverted. And therefore it can also used to associate lengths to covectors, or the inner products to covectors. So we can take this G inverse and act on two covariant vectors. Or in other words, it allows us to find a map between vectors and covectors. This is the usual thing that we have been doing all along. We can raise and lower the indices using the metric. So what it means is that we are taking an element of the tangent space and associate to that an element of the cotangent space, which are these covectors. So how do we do that? It's just the associated covector to a vector B is just what you would naturally expect when we lower the indices. Or if you want to write it in a more coordinate independent way, then let's call this, let's denote this covector as omega V, and this is defined as G acting on V as, or putting evaluating one of the slots of G with V. So now the other slot acts on a vector. So it is this object, this G of V, and this empty slot is a map from vectors to real numbers, which is exactly what a covector is. And then in components it's exactly that. If you like, here I can also put omega V mu. But it becomes very cumbersome, so we just call it V mu with lowering this. Yeah.
We define the vectors at first as operators on functions from that they give the derivative of the function.
Yeah.
In this one direction. Can we say something similar for the covectors? Do they act on functions too, or?
The similar thing that you can say about covectors is that they are maps from vectors to real numbers. So vectors are maps from functions to real number. And covectors are maps from vectors to real numbers.
Well, I could also say for the vectors that they are functions from forms to real numbers. Similarly.
Yeah.
Maybe I could also say for covectors that they can act on functions. Or maybe I can rephrase the question as, is there a connection between differential forms and what we are doing here? Taking the d of a function, exterior derivative, or whatever.
Yes, so these covectors are just one form. But one forms are not necessarily derivative of a function, are they?
It's different definition for one form.
But to define a one form, we need first to define what's a vector. Because usually it's the vector with a differential one form that we call one form in general. Is right? To define a form, we first need to define what's a vector.
Yeah, but that's what I did. I defined the one forms or covectors as the maps from vectors to real numbers. I don't think that one forms are always the exterior derivative of a function. Because I don't know how much you know about the forms of one property that so if a form omega is the derivative of a function, then so first of all, this would be already talking about form fields, because you can talk about forms without before even talking about fields, like the same way as in the case of vectors. You can talk about a vector before talking about vector fields. A vector can be just an entity that lives in the tangent space of a single point, while a vector field has to be an assignment of vectors, at least to a patch, if not to the whole manifold. Now functions, on the other hand, they are maps from the entire manifold into real number. So when we say omega equals df, we have already defined a form field that exists everywhere. While I can just talk about an omega that lives at the single point. So probably it's correct that there will be, for any omega, there will be, any omega that lives at the cotangent space of a point, there is a function so that df is given by, or omega is given by df. Yeah, I think that is correct. But it's not true that all form fields can be written as the exterior derivative of function, because for instance you might know that the derivative of, so this a form that is like that is called an exact form, and the derivative of an exact form is equal to 0. But clearly there are forms that whose derivative is not 0. For instance, when we consider electromagnetism, we can discuss it in the language of the forms. And then the vector potential A mu is a one form. And the field strength F is a two form given by exterior derivative of A, which is a one form. Obviously, F is not always 0. Therefore, A is not always derivative of something. Okay, let me just mention something about the embedding. So I actually phrased some of the discussions about the manifolds in terms of embedding. I talked about the sphere as being a two-dimensional surface in a three-dimensional Euclidean space. So in general, we can think about manifolds that are defined as some surface or hypersurface in one or more higher number of dimensions. Say that higher dimensional space, I parameterize it by big X A, where A runs from 0 to D, or 1 to D plus 1, depending on whether we are Lorentzian or Euclidean. And then we can define a manifold by putting a constraint on this XA. So what is the example? The example is the case of a sphere when we said x squared plus y squared plus z squared equals 1, which can be written in this form by taking 1 to the left-hand side. And so this condition allows us to get rid of one of the variables, one of the coordinates. So it naturally defines if we are talking about embedding a space which is D plus 1 dimensional, then this condition gets rid of one dimension, so we will end up with a D-dimensional manifold. So in this case, for instance, we are embedding a two-sphere in a three-dimensional Euclidean space, and this equation allows us to get rid of one of the variables. So it will be described by two variables. For instance, in this case, it can be described by theta and phi. So we can take x to be sine theta cosine phi, y to be sine theta sine phi, and z to be cosine theta. So these conditions, they guarantee that these equations are satisfied. So now we have a two-parameter theta and phi parametrization of the two sphere. So in particular, we know what is dxa, dx mu. Great. For me, x mu is now the set of theta and phi. Right. So these equations tells me what is this dxa dx mu, and this matrix it allows a natural mapping between various vectors and tensors, or in general the tangent and cotangent space of the two manifolds. So for instance, for any vector b mu that lives in our manifold, so say we are embedding, I think the sign that the mathematicians use is like that, embedding n in some other manifold n, and then if you have some vector b in some point, in some tangent space of a point of m, then we can connect it to a vector in the tangent space of n in the following way, by taking dA to be dxa dx mu times v mu. On the other hand, any covector or form in the embedding space defines a form in the actual embedded manifold. And again, this can continue. But one important object that one can consider is a metric. If you have a metric in the embedding space, then it will give us a metric in the embedded space, and that metric is called the induced metric. And that is something important. So we have G mu nu, which is the induced metric. One way to deal, of course, is basically this. But for instance, to derive it, once I have this mapping, to derive it, what I can do is to just substitute these relations in the lengths, in the interval, in the expression for the interval. So for instance, when we talk about 3D Minkowski, 3D Euclidean space, the interval is dx squared plus dy squared plus dz squared. And then we can substitute these expressions in here to find the induced metric. So after that substitution, what we get is ds squared of, so this is the ds squared of the Euclidean space. And then here we get the ds square of the sphere, two sphere. And that is just gonna be d theta square plus sine square theta times d phi square.
In all these objects, in both sides we have different number of components, right?
Yes. Yeah.
Like in one language, you just describe the things in terms of the angles, two angles, nothing else.
Mm-hmm.
But in the capital letters, you always have three components.
Mm-hmm.
So like we kind of lose information and we go from Euclidean metric that has three components to the induced metric, which is only two components. So it's like we lose something along the way.
Yeah, but the number of components.
I think there is also one extra condition. So I think two different variables in in two cases.
Which two are you referring to?
In Euclidean case, we have x, y, z, but there is also one condition which is sphere.
Uh-huh.
and so we have two components. But there is also two.
Yeah, so if I restrict to the surface of the sphere, then it's a two-dimensional manifold. In general, it's true that, for instance, if I consider a sphere, so I'm talking about a map between the tangent space of the sphere, say at the North Pole. So the tangent space will be some plane that I consider tangent to this North Pole. I'm talking about the map between vectors that live in this tangent space and the vectors that live in the tangent space of the Euclidean space at the same point. Of course, there is a different dimensionality of these two tangent spaces. This is a two-dimensional tangent space. And then we have the 3D Euclidean, which has a 3D tangent space. So I cannot span all of the tangent space of the embedding space using this. In particular, I can very easily give you an example. Take a vector that is perpendicular to the sphere. That vector exists in the tangent space of the 3D Euclidean space at that point, but does not live in the tangent space, or it maps to zero, corresponds to zero in the tangent space of the sphere. Yeah, I'm not sure what. There's clearly more objects that live in this ambient space, in the embedding space, than on the manifold. If that's what you mean by information.
Yeah, that's what I was meaning. But in terms of the manifold that you are interested in, the two pictures are enough to describe the manifold. Right?
Yeah. Other